Alright, this is your video for 4.6, and this is called CPCTC. Now I know that's not very easy to remember or say, but you'll get used to it. And it stands for corresponding parts of congruent triangles are congruent. So what happens is in 4.3, remember that when we had two triangles in 4.3, we had to prove all three sides were congruent. And then we had to prove all three angles were congruent. And that was a lot of work, and that was no fun. So then in 4.4 and 4.5, we got our shortcut. So instead of having to prove all three angles and all three sides, we said, for instance, okay, I could just use side, angle, side. Like this. And all I had to prove was side, angle, side, side, angle, side. Well, what happens then we said that's enough, these triangles can be considered congruent. Well, but then after that, we don't know anything about these angles, these other two angles, or this other side. So what we're going to do today is we're going to say, okay, so I can use my shortcuts and just use these three pieces, side, angle, side, 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 whichever one you need to use. But all I have to use is those three pieces. Then I can say, okay, the triangles are congruent by side, angle, side. Then I can say, okay, by CPCTC, I have to know that this other side then must also be congruent. So it's a way to get to talk about whichever piece of the triangle you want to, with still not having to go back to all three sides and all three angles. And now I can use the three that I can get to easiest, prove the triangles are congruent, and then prove that piece that I need after all. Okay, so it's just going to be one extra step here. Okay, and this is what this talks about here, and all it says is CPCTC uses congruent triangles to prove corresponding parts are congruent. So with the ones we've been doing in 4.4 and 4.5, we use the pieces to prove the triangles are congruent. Now we're kind of going to go backwards. We're going to use the triangles to prove the pieces are congruent. Okay, so a landscape architect sets up the triangles as shown in the figure to find the distance across JK, because JK is a pond, and obviously it's not easy to measure across a pond, so instead I measure everywhere else, and then I can figure out that. So how can we figure that out? Well, if we could know that these triangles were congruent, then I could just use the distance from M to N instead of getting wet wading across the pond. So let's prove that the triangles are congruent. So it's given that JL is congruent to LN, and that ML is congruent to LK, and we know angle JLK is congruent to angle MLN by vertical angles theorem. Therefore, the triangles, goodness sakes. The triangles would be congruent by side, angle, side. Side, angle, side. So now I can say that's what we've been doing for the last several days. So nothing's new with that. Now after I prove the triangles are congruent, I can say, well, then JK must be congruent to MN by CPCTC. So JK has to equal to 41 feet. Okay, so you can see that this is not going to be too much new information. All of this is old, what we've been doing the last several days. Now you can talk about any part of the triangle you want by CPCTC. So JK must be 41. Okay, let's move on. Okay, same thing. We're going to use the same kind of proofs as before. So YW bisects XZ. Okay, so YW bisects XZ. I can look down the proof and I can see the other given that XY is congruent to YZ down here. So I know I don't need to put them together. Definition of a segment bisector. Well, bisect means to cut in half. Therefore, I would know XW would be congruent to WZ. Okay, then it says I'm going to use the reflexive. So YW is congruent to itself. So I know that the triangles, let's see, triangle X, Y, W be congruent to triangle Z, Y, W. Make sure you name them in the right order. This is where some of you are going to get tripped up, because in all the other proofs, the proof statement was the triangle statement. So now we have to write this congruent statement ourselves, so we have to be careful that we write it in the right order. And as I tell you that, I did not. How about Z, Y, W? Okay, so this is what we've done for the last couple days. Now I just have to add this last step in here. Angle XYW is congruent to angle ZYW. XYW is congruent to ZYW by CPCTC. So hopefully by now you're seeing it. Everything's the same, and then once you prove the triangles are congruent, now I can talk about any other piece that I didn't already speak about by using CPCTC. Okay, so if you're good at your 4-4 and 4-5 proofs, then you have no problem with the 4-6 proofs. Okay, one more. NO is parallel to MP, angle N is parallel to angle P, and we want to prove that MN is parallel to OP. Okay, so looking down, I can see that I don't have any more room for any other givens, so I'm going to go ahead and put both of them together. So now we have seen this time and time again. When I have parallel, most of the time the very next step is going to be alternate interior. So this way I just have to prove what they are. So again, if you're still having a hard time seeing parallel lines cut by a transversal, go ahead and redraw over them, extend the lines, draw a separate picture outside. Do whatever you need to do to show you that we're talking about this angle NOM being congruent to angle PMO. So hopefully you can see that alternate interior there. MO is congruent to itself. We've seen that a million times. That's reflexive. Okay, so angle, angle, side, angle, angle, side, angle, angle, side. I just have to write my congruent statement. And again, I have to make sure I write them in the exact order in which they're congruent. So I'm going to say angle NOM is congruent to angle PMO. So be careful. It's very easy to want to put O and M in the same place, but they're not. The ones that are congruent, O is over here, M is over here. So don't be careful not to say POM, just to make it look like this one. Okay, so after that, now that the triangles, hello. Now that the triangles are congruent, I can say angle NMO, this guy, is congruent to angle POM, this guy, by CPCTC. Therefore, MN is parallel to OP by the converse of the alternate interior angles theorem. So what happened here is now I'm using these as parallel lines cut by a transversal. So now that changes. This is the alternate interior before. Whereas earlier I had it going this way. So these were my alternate interior. So it totally switched over who we were talking about just by switching which lines were your parallel lines. So when you're going backwards, when you're going from parallel to angles, that's regular alternate interior. When you're going from angles to parallel, that's converse, and that is from chapter 3. Okay, so you can use CPCTC with triangles that are on the coordinate plane in addition to just ones like in normal ones. So what you will do is you'll use the distance formula or Pythagorean theorem, and we just talked about this last week when no one knew how to do distance, was that Pythagorean theorem is easier, that you're going to use distance formula or really Pythagorean theorem to prove that the triangles are congruent by side, side, side. Because when a triangle is in a coordinate plane, that's all you can do is talk about his sides. There's no way for me to talk about his angles in a coordinate plane. So I'm going to talk about the sides, and I'm going to prove that it's congruent by side, side, side. And then CPCTC will allow me to talk about the angles and make sure those are congruent as well. Okay, so here we go. Here's are the given points, so we plot those, and I want to prove that angle DEF is congruent to angle GHI. But like we said a second ago, I can't talk about angles in a coordinate plane. All I can talk about is sides. So we're going to do the Pythagorean theorem 6 times to talk about all 3 sides. So let's get started. So GH. Again, Pythagorean theorem is easier. You just turn it to a right triangle and you count. Square root of 4 squared plus 2 squared. So is that 16 plus 4. Break that down. 2 and 10, 2 and 5. 2 on the square root of 5 for GH. HI is 1 and 2. That is the square root of 5. And GI is 3 and 2. So that would be 9 and 4 square root of 13. Okay, so now all I need to do is prove that that's the same as DEF. So DE is 4 and 2. So the good thing is I've already done that before. So 4 and 2 was 2 on the square root of 5 before, so it's 2 on the square root of 5 now. So GH is congruent to DE. Okay, EF, oops, I didn't mean that line, is 1 and 2. I've already seen 1 and 2 before. That's square root of 5. So HI is congruent to EF. And DF is 3 and 2. Seen that before. So that's square root of 13. So GI is congruent to DF. Therefore, triangle, now make sure you name them in order. So just go in the order you did these in. GHI is congruent to triangle DEF by side, side, side. So angle DEF is congruent to triangle GHI by CPC-TC. Because once the triangles are congruent by side, 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 then I can use CPC-TC to say, okay, that means this angle is congruent to this angle. And I didn't have to get out a protractor or any of that kind of stuff. All right, see you tomorrow or Monday.